Hello, everyone. So, we're going to talk about the last topic for your midterms before your term examination, which is the chemistry of lipids. I am Nicolay Lumawan Martin, one of your faculty of medical laboratory science or medical technology of the University of St. Louis. So, we're going to talk about lipids. But before that, let's try to lay down the different learning outcomes or objectives in this topic. So we have to identify the different classification of lipids. We also have to describe the different biomedical importance or functions of lipids. We have to describe in detail about the chemistry and function of lipids. And lastly, we have to discuss the physical and chemical properties of lipids. So we define or we term lipids as biological molecules that are insoluble in water but soluble in nonpolar solvents. Again, kindly take note or kindly highlight insoluble in water but soluble in nonpolar solvents because our lipids now have a wider spectrum of compositions and structures because they are defined in terms of their physical properties, which is their water solubility. Therefore, lipids are marginally insoluble at best in water, but readily soluble in organic solvents. Again, they are marginally best or marginally they are insoluble at best in water but readily soluble in organic solvents. What are types of different organic solvents or organic substances? We have chloroform, for example, or we also have acetone. So our lipids are the waxy, greasy, or oily compounds that are found in plants and animals. So next is we're going to talk about the different biomedical importance or functions of lipids. First important function of lipids is it serves as or it acts as an energy source. When we say energy source, our lipids therefore acts as fuels in the body. So lipids are found to be superior to carbohydrates and proteins in providing energy to the body with respect to their energy release by the process of oxidation. Again, it has been found that our lipids are found to be superior to carbohydrates and proteins in providing energy. So, this is all about energy release by the process of oxidation because lipids now can actually yield 9.5 kilocalories per gram. Whereas, if we try to compare it with our proteins and carbohydrates, they only yield at about 4 kilocalories per gram. So there is really a big difference in terms of energy released by their oxidation. Another function of our lipids or biomedical importance is lipid storage. So since lipids are insoluble in aqueous solutions, they can be stored easily in the body. So they can be stored in the body in almost unlimited amount in contrast to our, for example, our carbohydrates, which is stored in limited amounts in places. So that's another function of our or of our lipids, I should say. It is for lipid storage. It's also important for insulation or heat insulation because fats are usually stored in the subcutaneous layers or the subcutaneous tissues. Therefore, they exert insulating property. So, insulation or this insulating property of fats or our lipids in general is found to be very useful, especially in those animals living in the cold climate. Like for example, we have whales and other uh, animals in the cold climate. So lipids now stored around are stored around internal organs are found to be padding and it also serves as a protection for these different internal organs. So it's also important for insulation. Another function is structural role. So as we have seen in the picture a while back, in the previous slide, you can see actually the cell membrane. So lipids therefore play a very vital role now in structure by being an important component of the cell membrane. as we have tried to go back to the topic of cell biology in our prelims, we have been continuously reiterating that our cell membrane is actually a lipid bilayer. Okay, so when we say structural role or structural component, that is one of the function of lipids. Especially, we have the phospholipids and cholesterols. They are important for structural role or function. Aside from structural role, we also have endocrine functions. So when we say endocrine, what comes into our mind is hormones. Hormones like adrenocorticoids, mineralocorticoids, we have sex hormones, and also vitamin D. They were found to be synthesized from lipids like cholesterol. So it's also important for endocrine function. And since you have mentioned about vitamin D, it's also important for vitamin absorption. So as we know, or we have as a general knowledge, we know that there are actually fat soluble vitamins. So our lipids now are essential for the absorption of the so-called fat soluble vitamins. What are these fat soluble vitamins? We actually have a mnemonics here. We have ADEC. So we have the fat soluble vitamins A, D, E, and K. So we're going to dive deeper, or we're going to discuss further about vitamins once we go through our finals. And aside from vitamin absorption, lipids also has an important or biomedical importance in our nervous system, because lipids now are found to be important constituent of the nervous system, because our nerve cells now contain greater amount of lipids, and with that, they play, therefore, a vital role in nerve cell insulation and impulse conduction. Again, the biomedical importance of lipids in nervous system is that since it is found as one of the major constituent of the nerve cells, therefore, it plays a vital role in nerve cell insulation and impulse conduction. And lastly, we also have one of the biomedical importance or function is antibiotic activity. In antibiotic activity, we have a specific type of steroid, which is, we call it as squalamine or Squalamine. Squalamine now is a steroid from shark's blood, and it has been found to have an antifungal and antibacterial activity. So that is squalane. So those are the different biomedical importance of our lipids. So for energy source, for lipid storage, for insulation, for structural role or structural component, for endocrine function, for vitamin absorption, for nervous system, and lastly for antibiotic activity. Next is we have the Bloor's criteria. When we say Bloor's criteria, these are now sets, or these are set of principles for assessing the credibility of scientific evidence. So there is actually no single internationally accepted system to classify now the different lipids available. So the name or the different names of compounds, however, do fall in certain categories, such as we have the component structures, and the Bloor's classification is generally adopted with a few modifications, such as they are insoluble in water, the solubility in one or more organic solvents, such as ether, chloroform, benzene, acetone, which are generally called as fat solvents. Some relationship to the fatty acids as esters are either actual or potential, and the possibility of the utilization by living organisms. Thus, lipids includes, we have fats, oils, waxes, and related compounds. So in the classification of lipids, can actually classify them based on their composition and based on their component structures. So based now on this picture or flow chart, lipids can be classified as either simple, complex, derived, or miscellaneous. So when we say simple lipids, we actually have subdivisions or subclassifications. We have fats and oils and waxes. For complex, we have four. We have the phospholipids, we have the glycolipids, sulfolipids, and lipoproteins. For derive, we have actually fatty acids and alcohols. And for miscellaneous, we have our aliphatic hydrocarbons and terpenes. Aside from classifying them based on the component structures, we can simply classify lipids based on the composition. They are divided into two. We have the saponifiable lipids and the non-saponifiable lipids. When we say saponifiable lipids, they contain esters which can undergo the process of saponification. What is the process or what is saponification? When we say saponification, that is already the hydrolysis under basic conditions. Again, that's hydrolysis under basic conditions. Therefore, the examples under the saponifiable lipids, we have waxes, we have the triglycerides, phosphoglycerides, sphingolipids, and we also have the glycerolipids. So again, when we say saponifiable lipids, they contain esters and they undergo the process of saponification. Another classification is we have the non-saponifiable lipids. From the word non-saponifiable, therefore, they do not contain ester or ester groups and cannot be saponified. So example of those non-saponifiable lipids are we have the steroids and we have the prostaglandins. So next is we're going to dive deeper on the classifications based on the component structures. So when we say simple lipids, they contain two types of components. So simple lipids are esters of fatty acids with various alcohols. So they only contain mainly fatty acids or a fatty acid and alcohols alone or alcohol. So when we try to look into simple lipids, that's basically a fatty acid and an alcohol. So they are further divided into two classes. Namely, we have the neutral fats and waxes. So when we say neutral fats or triglycerides, they are triesters of fatty acids with glycerol. Kaya nga, another term for our neutral fats or another term as well for our triglycerides is triacyl glycerol. So they are just the same. Neutral fats, triglycerides, triacyl glycerol because they are basically triesters of fatty acids with glycerol. And we also have under lipids or simple lipids, we have waxes. So waxes naman, they are esters of fatty acids with higher mono hydroxyaliphatic alcohols. True waxes, cholesterol esters, and vitamin A and D esters are example of waxes. So these are the different types of simple lipids. Next is we have the complex or compound lipids. So they contain more than two components. We have the fatty acids, an alcohol, and other components. So they are the esters of fatty acids, which contains groups other than and in addition to an alcohol and fatty acids. So under compound lipids, as we have mentioned, we have the phospholipids, the glycolipids, we also have the sulfolipids and the lipoproteins. So for phospholipids, just an overview. So in addition to fatty acids and alcohol, they also contain now phosphorus, for example, nitrogenous bases, and other substitution groups. So that is for our phospholipids. Examples of our phospholipids, therefore, would be our lecithin and cephalins. These are examples of phospholipids. Aside from phospholipids, under compound or complex lipids, we also have the glycolipids. From the word glyco, these are lipids now that contains carbohydrates. And therefore, the word itself, they are referred to as glycolipids. They contain an special alcohol moiety called the sphingosine or sphingol and a nitrogenous base, and they do not have phosphorus unlike for our phospholipids. So examples of our glycolipids is we have the gangliosides and the cerebrosides. Then we also have s- sulfolipids. So sulfolipids therefore contain sulfate groups. That's why they are referred to as sulfolipids. And we also have the lipoproteins. For lipoproteins, when lipid contains now protein, then they are of course known or referred to as lipoproteins. The examples of lipoproteins, we have the chylomicrons, we have the VLDL, LDL, and HDL. So we will discuss further of those different types of classifications as we go through the topic. And of course, we have the derived lipids. Lipids are derived from lipids or precursors of lipids. So they are obtained upon the hydrolysis, therefore, of simple and complex lipids, and still they retain the characteristic of lipids. Though, so they are classified further, no, under the derived lipids, they are classified further into uh, two types, which we have the fatty acids and we also have the uh, alcohols. So lastly, we have the miscellaneous lipids. So miscellaneous lipids are those lipids which cannot be grouped under any of the above classifications. So they include now our aliphatic hydrocarbons, our terpenes, and carotenoids. So we also have squalene and we have vitamin E and K. So those are the different classifications of lipids based now on component structures. Next is we're going to dive deeper on the simple lipids. So as we have mentioned a while back, our one of the subclassifications of our simple lipids would be our neutral fats, or they can be termed as triglycerides or triacylglycerol. So triesters of trihydric alcohol, glycerol with various fatty acids, naturally occurring fats that have apparently the D structural configuration, and they can be emulsified. When we say emulsified, therefore, they undergo now the process of emulsification. Emulsification of fats may be made by shaking very vigorously in water and by emulsifying agents such as we have gums, soaps, and proteins, which produce now more stable emulsions. So the biomedical importance of emulsification is that the emulsification of different dietary fats in the intestinal canal, actually brought about by bile salts, is a prerequisite now for digestion and absorption of fats. So, again, our neutral fats or triglycerides and triacylglycerol can be emulsified. So, depending upon the fatty acid residues in glycerol, there are actually two types of fats. Namely, we have the simple triglycerides and we also have the mixed triglycerides. So, please take note of that. Again, depending now on the fatty acid residues, we can classify, subclassify our neutral fats or triglycerides or triacylglycerol into simple triglycerides and mixed triglycerides. Next is we have our fats and oils. So the fatty acids in triglyceride molecule are usually not all the same. So natural triglycerides are often mixture of many different triglyceride molecules. Fats are triglycerides that are solids at room temperature. So fats are usually derived now from animal sources and mostly they are saturated. On the other hand, our oils now are actually triglycerides that are liquids at room temperature. So oils therefore are derived now from plant sources or fish, and they are mostly unsaturated fatty acids. Again, if we try to differentiate fats and oils, fats are solid at room temperature. On the other hand, our oils are liquid at room temperature. Based on its sources, usually fats are derived from animals, On the other hand, oils are usually derived from plant sources and fishes. And based on their um, whether they are saturated or non-saturated or unsaturated, mostly saturated fatty acids are fats, and oils are mostly unsaturated fatty acids. Next is we also have our waxes. So waxes are simple lipids that contain a fatty acid joined to a long chain of about 12 to 13 carbons alcohol. So they are insoluble in water and they are not as easily hydrolyzed as fats and oils. They often occur in nature as protective coatings on feathers, fur, I should say, skin, leaves, and fruits. So waxes, for example, sebum, aside from those that have been mentioned, as protective coatings. For example, our sebum or sebum, they are secreted now by our sebaceous glands of the skin. If we try to have an review again or a recall of your anatomy and physiology with pathophysiology, specifically on your integumentary system, we have the sebum, which is secreted by the sebaceous gland of the skin. They contain now, I should say, waxes that help to keep the skin soft and prevent dehydrations. So aside from that, our waxes are actually used now commercially to make cosmetics. Aside from cosmetics, we also have candles, ointments, and protective polishes. So next is we're going to talk about the properties. For the properties, our neutral fats are usually colorless. Aside from colorless, they are odorless and tasteless substances. The color and taste of some of the naturally occurring fats is due to the extraneous substance. Aside from that, they are insoluble in water but soluble in organic fat solvents. The specific gravity of all fats is less than 1.0. Consequently, all fats float in water, and it undergoes emulsions and saponification. It also undergoes hydrolysis, additive reactions, and oxidations. And it may or may not undergo rancidity depending on uh, components. So let's focus more on the concept of rancidity. So again, it may or may not undergo rancidity depending on the components. When we say rancidity, we're talking about unpleasant odor and taste developed by most natural fats on aging. So, in order for us to prevent rancidity for vegetable fats, they contain certain substances like vitamin E. Aside from vitamin E, we have the phenols, we also have the hydroquinones, tannins, and others or other components which are antioxidants, and therefore they prevent the development of rancidity. Hence, the different vegetable fats, they are preserved for longer period of time as compared to animals. Again, when we talk about rancidity, it may or may not undergo rancidity, or there is a presence of unpleasant odor and taste developed by most natural fats when they age. Our vegetable fats actually contain certain substances that serves now as an antioxidants, and therefore it prevents rancidity. So as compared now to our animal fats, they have longer periods of preservation. So those are the different types of simple lipids. Now we're going to talk about our complex lipids. First of the complex lipids is we have the phospholipids. So again, we contain, in addition to fatty acids and glycerol or other alcohol, a phosphoric acid residue, nitrogen containing base, and other substituents. For the classifications of phospholipids, we have the following. We have the glycerol phosphatids or phosphatides, we have the phosphoinositides, and we have the phosphosphingosides. So our glycerol phosphatides, in this glycerol is the alcohol group. Examples, we have the phosphatidyl ethanolamine or the cephalin. We also have phosphatidylcholine, which is the lecithin, phosphatidylserine, plasmalogens, I should say. We have the phosphatidic acid, cardiolipins, and the phosphatides. For the phosphoinositides, in these groups, we have inositol on its alcohol. Example, we have the phosphatidyl inositol or we have the lipositol. And we also have the phosphosphingosides. These are the alcohol present here naman are the sphingosine or sphingosine, which is also called as sphingol. So, and it is an unsaturated amino alcohol. Example now is we have the sphingomyelin. So those are classifications of should say these are classifications of phospholipids. When we say phosphatides, uh, the alcohol group is the glycerol. When we say phosphoinositides, we have inositol as alcohol group. And when we say phosphosphingosides, we have sphingosine, or we can also call it as sphingol as alcohol group. So let's focus on the phosphosphingosides. So we'll try to correlate it on its clinical aspect. So we actually have this disease which we call as Niemann-Pick disease. Niemann-Pick disease is actually a deficiency of a certain enzyme. And this enzyme is what we call now as the sphingomyelinase. Again, it's called as the sphingomyelinase, which is a lysosomal enzyme. Again, I'd like to reiterate on the phosphosphingosides. We try to correlate it with a clinical aspect or a disease which we call as the Niemann-Pick disease. Niemann-Pick. Niemann-Pick disease in which there is a deficiency of the enzyme sphingomyelinase, which is a lysosomal enzyme. Usually, Niemann-Pick disease affects children that arises at birth or infancy. So what happens? These children um, inflicted with the disease presents gradual enlargement of the abdomen. Aside from the gradual enlargement of the abdomen, there is also hepatomegaly. When we say hepatomegaly, there is also an enlargement of the liver. Aside from hepatomegaly and the gradual enlargement of abdomen, there is also splenomegaly or splenomegaly. When we say splenomegaly, there is therefore an enlargement of the spleen. And aside from that, there is a manifestation of progressive mental deterioration. So those are the different signs and symptoms that are presented or the clinical manifestations on Niemann-Pick disease. There is again an enlargement of the abdomen, there is hepatomegaly, splenomegaly, and there is also a manifestation of progressive mental deterioration. Bakit po nagkakaroon ng ganon? This is due to the accumulation now of sphingomyelins in the brain. Other lipids and cholesterols are usually normal in these individuals or patients or maybe slightly elevated. And usually, individuals diagnosed with Niemann-Pick disease have a prognosis that is, unfortunately, usually fatal progressive downhill course. So, over 80% of patients or specifically infants die within 2 years when they are diagnosed with Niemann-Pick disease. So that is one of the clinical aspect or correlations. Again, we have the Niemann-Pick disease in which this is a deficiency of the enzyme sphingomyelinase, which is a lysosomal enzyme. So it usually affects children that arises at birth or infancy. Next, is we're going to talk about phospholipids of biomedical importance. So we have the phosphatidylcholine or the lecithin, and we also have the phosphatidylethanolamine, which are the cephalins. So phosphatidylcholine or lecithin now, they are widely distributed in animals, specifically in the liver, brain, nerve tissues, sperm, and the egg yolk. So lecithin is a multi-purpose food ingredient as well that primary functions as emulsifier and dispersing agent. And we also have, of course, our cephalins. Cephalins are structurally identical with lecithins and are found in most cell membranes, particularly in our brain tissues. So they are important in blood clotting and specifically in they are found now in blood platelets. So those are the different phospholipids of biomedical importance. Next, now is we're going to talk about our glycolipids. For glycolipids, we actually have the first one, we have the cerebrosides or our glycosphingosides. So these types of glycolipids or glycosphingolipids are found primarily in the brain and in the peripheral nervous tissue. Again, they are found usually in the brain or primarily in the brain and in the peripheral nervous tissue. It acts now as an insulator and is mainly involved in providing a protective coating to the nerve tissues. So there is no glycerol, no phosphoric acid, and no nitrogenous base. Thus, a cerebroside on hydrolysis will yield a sugar, which is usually galactose, but sometimes glucose. You also have a high molecular weight fatty acid and an alcohol. So sphingosine or the dihydrosphingosine. So again, in hydrolysis, since there are no glycerol, no phosphoric acid, and no nitrogenous base, what is the expected um, uh, different components of a cerebroside? We have the sugar that is usually galactose or sometimes glucose. We have fatty acids, which are usually high molecular weight fatty acids, and alcohol, which is the sphingosine or sphingosine or the dihydroxysphingosine. So for the clinical aspect, I should say, we try to correlate cerebrosides to or glycosphingosides with the clinical aspect. And we actually have another disease, which is the Gaucher disease. Gaucher's disease, Gaucher's, Gaucher's disease. So this is an inherited disorder of the cerebroside's metabolism. Again, it is an inherited disorder of cerebroside's metabolism. So there is a deficiency of again of another enzyme, which is the beta glucocerebrosidase. Again, in Gaucher's disease, there is again a deficiency of a certain type of enzyme, I should say, which is the beta glucocerebrosidase. So usually in infancy and childhood, the signs and symptoms are fairly acute onset with rapid course and death in several years. So for patients who are infants and who are children, they experience progressive mental retardation. So again, that is the signs and symptoms or the clinical manifestations of individuals who are or patients that are infants and children. They usually have progressive mental retardation. In adults, there is splenomegaly. So there is a progressive enlargement of the spleen, which may reach to umbilicus or below the umbilicus. Again, there is enlargement of the spleen, progressive enlargement of spleen or splenomegaly. Characteristic bone pain also due to marrow cells replaced by histiocytes loaded with the lipids and with the this replacement of histiocytes and since they are loaded with lipids as a result, they lead also to progressive anemia, leukopenia, and you also have thrombocytopenia. Again, Gaucher's disease for adults, they experience splenomegaly. They will also experience uh, progressive anemia, leukopenia, and thrombocytopenia. cytopenia. So that is the clinical aspect now of our Gaucher's, for our, I should say, cerebrosides, which is the Gaucher's disease. Next is we also have our gangliosides. So gangliosides are types of glycolipids or glycosphingolipids that are neutral compounds and are composed of sialic acid residues. They are the main components of the animal cell membrane and are abundantly found in the plasma membrane of the neuron. So on hydrolysis, gangliosides will yield of the following. There is a long chain of fatty acids, which are usually from carbon 18 to carbon 24, alcohol, which is the sphingosine or sphingosine, a carbohydrate moiety, which usually contains the following. It's either a glucose and or galactose, one molecule of N-acetyl galactosamine, and also we have the molecule of N-acetyl neuraminic acid, which is also called now as our sialic acid. So for our gangliosides, we actually have at least two um clinical aspects. First is we have the disease which we call as GM1 or the gangliosidosis or gangliosidosis. So gangliosidosis or GM1 is due to a deficiency of the enzyme beta-galactosidase. So again, there is a deficiency of the enzyme beta-galactosidase. That leads now to the accumulation of GM1 gangliosides, glycoproteins, and the mucopolysaccharide, which is the keratan sulfate. Again, there is an accumulation of gangliosides, glycoproteins, and keratan sulfate. That is gangliosidosis. We also have GM2 gangliosidosis, which we call now as the Tay-Sachs disease. Tay-Sachs, Tay-Sachs disease or GM2 gangliosidosis. On this type of disease, there is an accumulation of gangliosides in brain and nervous tissues. So the affected ganglioside here is GM2. So in Tay-Sachs disease, there is a deficiency of hexosaminidase A. Okay? Hexosaminidase A is the deficiency for Tay-Sachs disease or GM2. For GM1 gangliosidosis, there is a deficiency of beta-galactosidase. So for our Tay-Sachs disease, this is actually a rare inherited disorder which is associated with progressive development of idiocy and blindness in infants soon after birth. So there is mental retardation, progressive mental retardation, and blindness for infants. Aside from that, there is also a scene in the eye or ophthalmoscopically, we can see a cherry red spot about the mascula in the eye of the patient. Again, there is a cherry red spot about the macula, I should say, of the patient ophthalmoscopically or when we try to observe its eye. And aside from that, there may be seizures and association of macrocephaly. So again, usually for these individuals who have a deficiency of the hexosaminidase A or the Tay-Sachs disease, they can develop or they can have progressive development of idiocy and blindness, especially in infants soon after birth. Ophthalmoscopically, there is an observation of a cherry red spot about the macula, and there can also be seizures and also association of macrocephaly. Therefore, in this disease, prognosis is actually bad, and unfortunately, it usually death follows after being diagnosed with this disease. Again, for the clinical aspect of our ganglioside, we actually have two. We have GM1 gangliosidosis, which is there is a deficiency of the beta-galactosidase, and you also have Tay-Sachs disease or GM2 gangliosidosis, in which there is a deficiency of hexosaminidase A. Next is we have our sulfolipids. For our sulfolipids, these are lipid materials containing sulfur, from the word sulfolipids or sulfates, that has long been known to be present in various tissues and has been found in liver, kidney, testes, brains, and certain tumors. The failure of degradation of these compounds will result now to accumulation of these complex lipids in our central nervous system. Then we also have our lipoproteins. For our lipoproteins, uh, these are particles made of fats or lipids and proteins that travel in your bloodstream to cells throughout your body. Cholesterol and triglycerides are two types of lipids found in lipoproteins. There are actually five types of lipoproteins in which a while back we have actually dictated. We have the HDL, the LDL, the VLDL, we also have the IDL, and we have the CM or the chylomicrons. So for the HDL, or high density lipoprotein, they are actually referred as good cholesterol. Why? Because this cholesterol, it carries now, or I should say, this lipoproteins actually carries cholesterol back to your liver to be flushed out of your body. So therefore, that's why it's called as good cholesterol, because high levels now of HDL will reduce the risk of having cardiovascular disease or heart diseases. Okay? So what is the mechanism of our HDL again? Why is it called as good cholesterol? Because our lipoprotein HDL or high density lipoprotein will carry the cholesterol back to your liver, and then it will be flushed out to our body. So therefore, the correlation later on of high levels of HDL will reduce the risk of a patient or an individual to actually have uh, CVDs or cardiovascular disease or heart diseases. Next is we also have our LDL or our low density lipoprotein. Uh, for our low density lipoprotein, if we term HDL as good cholesterol, our low density lipoprotein are actually termed or coined as bad cholesterol. Why? Because it increases now your risk of coronary artery diseases, heart attacks, and strokes. Because what happens? Our lipoprotein LDL or low density lipoprotein actually carries cholesterols that accumulates as plaque inside the blood vessels. Therefore, since there is an accumulation of cholesterol in the blood vessels, this plaque buildup can actually make the blood vessels too narrow for the blood to flow freely. And this condition is what we call now as atherosclerosis. So that's why LDL is termed as bad cholesterol, because LDL will now carry the cholesterol that accumulates as plaque inside the blood vessels. So that is our low density lipoprotein. Next is we also have the very low density lipoproteins. It is another type of bad cholesterol. Our VLDLs carry naman our triglycerides or our triacylglycerol. And to a lesser degree, cholesterol to your tissues. So they are another type of bad cholesterol. We also have here IDL. These are intermediate density lipoproteins, which are created when VLDLs or very low density lipoproteins give up their fatty acids. And we also have our CMs or our chylomicrons. They are very large particles that are also transport our triglycerides. They're then either removed by your liver or they are converted into your low density lipoprotein. So those are the different types of lipoproteins. Now we go to our derived lipids. For our derived lipids, we have first our fatty acids. So fatty acids are organic acid that occurs in a natural triglyceride and is a monocarboxylic acid ranging in chain length from carbon 4 to about 24 carbon atoms. So our fatty acids are obtained now from the hydrolysis of fats. We actually have different types of fatty acids. We have the straight chain fatty acid, we have branch chain fatty acids, we also have substituted fatty acids, we have cyclic fatty acids, and we have the eicosanoids. So first one is we have the straight chain fatty acids. For the straight chain fatty acids, we have the saturated and the unsaturated fatty acids. So the cis double bonds in unsaturated fatty acids put an inflexible kink in the carbon chain, preventing the molecules from packing together as tightly as saturated fatty acids do. So, for example, for saturated, we have the stearic acid. Stearic acid. For one double bond, we have the oleic acid. And you also have for two double bonds, we have the linoleic acid. All have 18 carbons in chain, but their melting points are drastically different. So saturated fatty acids have a general formula now of CnH2n plus 1COOH. So saturated fatty acids having 10 carbon or less number of carbons are called as the lower fatty acids. Again, fatty acids, saturated fatty acids that have 10 carbons or less number of carbons are called as lower fatty acids. Example, we have the acetic acid, we have the butyric acid, etc. Saturated fatty acids, on the other hand, that have more than 10 carbon atoms are called now higher fatty acids. Example of higher fatty acids is we have the palmitic acid. We also have the stearic acid. So, and others. So, please take note that our milk actually contains significant amounts of lower fatty acids. Again, when we say saturated fatty acids that have 10 carbons or less than 10 or less number of carbon atoms, these are called as the lower fatty acids. Saturated fatty acids having more than 10 carbon atoms are called as the higher fatty acids. So these are the a table presenting now the number of carbon atoms, the different common names, and the systemic name, and also the formula for the different acids or fatty acids. So just go over with that certain table. Next is we have our unsaturated fatty acids. Unsaturated fatty acids are classified further according to their degree of unsaturation. So examples, we have the oleic acid, linoleic acid series, linoleic acid series again, and we also have the arachidonic acid series. So these three polyunsaturated fatty acids are called now as essential fatty acids. Again, linoleic acid series, and arachidonic acid series, these three polyunsaturated fatty acids are called as essential fatty acids because they have to be provided in the diet as they cannot be synthesized in the body. So again, this have to be provided, they have to be provided in the diet as they cannot be synthesized in the body. So these are the table of the different monounsaturated and the polyunsaturated fatty acids. Just go over with this. And now we're going to talk about the properties of fatty acids. So for fatty acids, they are long, nonpolar hydrocarbon tails of fatty acids are responsible for most of the fatty or oily characteristic of lipids. The carboxyl or the COOH group is hydrophilic under basic conditions such as the physiological power of hydrogen or pH is 7.5. We also have here the fatty acid micelles. So in aqueous solutions, fatty acids associate with each other in spherical clusters, in which this is seen in the figure or picture. This is called as micelles, in which the hydrocarbon tails tangle each other up through dispersion forces, leaving now a shell of polar carboxylate ions facing outwards in contact with water. So again, there is a formation of shell, okay? And this micelles now, therefore, the tails are inside, they are called as hydrophobic groups. The heads are called as the hydrophilic groups. They are in contact with water. The micelles now, which are spherical clusters, are important in transport of insoluble lipids in blood and in the actions of soaps. Again, fatty acid micelles are important in the transport of insoluble lipids in blood and in the actions of soaps. Other characteristics of fatty acids, they are usually they usually, I should say, have straight chains, so no branches that are about 10 to 20 carbon atoms in length. They usually have an even number of carbon atoms. Carbon chains may be saturated if all of them are single bonds, or unsaturated if they contain double bonds. Other than carboxyl group and the double bonds, there are usually no other functional groups. Shorter fatty acids, of course, have lower melting points than the longer ones. For example, our stearic acid, 70 degrees Celsius. For palmitic, it's 63 degrees Celsius. And the double bonds are usually in cis configurations. For the branch chain, fatty acids, I should say, they are odd and even carbon branched chain fatty acids occur in animal and lipids. Example, we have the sebaceous glands. So the sebum or the sebum contains now branched chain fatty acids. And then we also have branched chain fatty acid is present in foods. So we have here in the figure, we have the phytanic acid. We also have the pristanic acid, and we also have the 4,8,12 trimethyl tridecanoic acid. So our phytanic acid, this is usually seen in butter. So phytanic acid, butter. For pristanic acid, it's also found in the lipids from many sources, such as for pristanic, we have freshwater sponges, we have krill, earthworms, whales. Also, you can see pristanic acid in human milk, and we have the bovine depot. So those are the different sources for pristanic acid. And lastly, for 4,8,12 trimethyl tridecanoic acid, they are seen in the extracellular membrane. So those are the different branch chain fatty acids. Next is we have the substituted chain fatty acids. In hydroxy fatty acid and methyl fatty acid, one or more of the hydrogen atoms have been replaced by an alcohol group or CH3 group respectively. So both saturated and unsaturated hydroxy fatty acids, particularly with long chains, are found in nature. Examples are we have the cerebronic acid of brain glycolipids, and we have resinolic or ricinoleic acid in castor oil. So those are different substituted fatty acids. We also have cyclic fatty acids. These fatty acids, varying cyclic groups are present in some seeds. So for example, we have the cholmoogric acid, also have the hydnocarpic acid, and the gorlic acid. So kindly take note of the chol or Greek acid. They are usually obtained now from the Chol moogra seeds. CHAULMOOGRA. Chol moogra seeds. Again, cholmoogric acid are usually obtained in the cholmoogra seeds. On the other hand, our hydnocarpic acid, are also found in plants now of the genus Hydnocarpus. Again, they are found in the genus Hydnocarpus. Okay? So both were solmoogric acid and hydnocarpic acid, both of them have been used earlier for long time for the treatment now of leprosy. Again, solmoogric acid and hydnocarpic acid, they are both used in the earlier times as a treatment for leprosy. Okay? So those are the different cyclic fatty acids. Now we're going to talk about eicosanoids. Eicosanoids now, these are derived from eicosapolenoic acid, or I should say eicosapolenoic fatty acids. So we have our prostanoids, we have our leukotrienes, and we also have our lipoxins. They are active lipid mediators that regulate inflammatory response. So yung prostanoids natin, they are seen to target the NSAIDs, or when NSAIDs are the non-steroidal anti-inflammatory drugs, which allow for therapeutical potential. Again, our prostanoids are usually seen in our to target now our non-steroidal anti-inflammatory drugs, which allow for therapeutic potential. For prostanoids as well, they are present within areas of the body, such as we can see prostanoids in our GI tract or our gastrointestinal tract. We also have the urinary tract. We also have the respiratory and the cardiovascular system. Aside from those, we also have the reproductive tract and the vascular system. Again, our prostanoids are present within the areas such as we have the GI tract, we have the urinary tract, respiratory, we also have the cardiology or cardiovascular system, we have the reproductive tract and the vascular system. Aside from that, our protenoids can be seen with the aid of water and ion transportation within cells. And prostanoids now helps the release of our prostaglandins upon activation. Receptors may open possibilities for treatments within different systems. So again, that's prostanoids. They are seen to target on our NSAIDs, which allows now for therapeutic potential. So eicosanoids. Next is we have our miscellaneous lipids. For our miscellaneous lipids, this includes now compounds which actually contain characteristic of lipids. They include our squalene, our terpenes, hydrocarbons, and our carotenoids. So in animals, supplementation of the diet with squalene can reduce actually cholesterol and tag or triglyceride levels. So our miscellaneous lipids are those that are uh, again they include compounds which can contain characteristic of lipids. So based on function classification of lipids, we have the storage lipids, we have the triglycerides, and we have the waxes. For structural, we have the phosphoglyceride, sphingolipids, glycolipids, and sterols. And for lipids as signals, cofactors, and pigments, we have the steroid hormones, prostaglandins, and the otacoids. Otacoids are lipid derived. Then based on composition, we have mentioned we have the saponifiable and the non-saponifiable. Again, if it's saponifiable, it contains esters and it can undergo saponification. On the other hand, for non-saponifiable, it does not contain ester groups and cannot be saponified. So steroids are classified as lipids because they are insoluble in non-polar solvents, but they are non-saponifiable because the components are not held together by esters or by ester linkages. So this is the basic steroid structure. They contain actually a 4 fused rings. Next is we have our cholesterol. Our cholesterol is actually considered as the most abundant steroid in the body. So it's an essential component of cell membranes and it is a precursor for other steroids, such as we have the bile salts, the sex hormones, the vitamin D, and the adrenocorticoid hormones. So there is apparently a correlation between high levels of cholesterol in blood with atherosclerosis, in which we have discussed a while back. Then we also have our bile salts. Bile are basically yellowish brown or green fluid produced in the liver and stored in the gallbladder. So the bile salts act like soaps and other emulsifiers. They contain both polar and nonpolar regions, helping tone break fats in food into smaller pieces, allowing them to be hydrolyzed more easily. For the clinical aspect of our bile salts, we have what we call now as gallstones because bile salts emulsify cholesterol in the bile so it can be removed in the small intestine. So if the cholesterol level are too high or it's elevated or the levels or of the bile salts is too low, the cholesterol precipitate forms now gallstones. And these gallstones, the formation of gallstones the can actually block the duct that allows the bile to be secreted into the duodenum. So therefore, since there is a blockage, the fats are no longer digested properly, and the bile pigments absorbed into the blood can cause the skin to become yellowish or yellow, and the stool to become gray. Okay? So that what happens when a person actually have gallstones. Again, gallstones can block the duct that allows the bile to be secreted into the duodenum. Therefore, the fats are no longer digested properly, the bile pigments are absorbed into the blood, causing the skin to become yellow or yellowish in color, and the stool will become gray. So those are the clinical correlations or the clinical aspect for our bile salts. Next is we also have our vitamin D. So our vitamin D is also termed as the sunshine vitamin because it is needed for calcium absorption. So what are the precursors? We have 7-dihydrocholesterol to cholecalciferol or vitamin D3 and ergosterol to ergocalciferol or vitamin D. Then we also have our steroid hormones. For steroid hormones, we have adrenocorticoid hormones. The adrenocorticoids or adrenocorticoid hormones are produced in the adrenal glands. So they are located now on the top of the kidneys. So glucocorticoids such as cortisol will affect now the metabolism of carbohydrates. And cortisol and its derivatives, cortisone and the prednisolone, which is synthetic, are powerful anti-inflammatory drugs used for the treatment of arthritis and asthma. Kindly take note of that. But before that, again, when we talk about hormones, just a review or recall, hormones are chemicals now that are released by cells or glands in one part of the body that will send out now signals or messages that will affect cells in other parts of the body. So mainly or many usually of our hormones are steroid hormones. And again, adrenocorticoid, specifically we have the glucocorticoids, they are we have the cholesterol that will affect now the metabolism of carbohydrates. So the cortisol and its derivatives, cortisone, prednisolone, they are again, kindly take note that they are powerful anti-inflammatory drugs used to treat or for the treatment of arthritis and asthma. We also have mineralocorticoids. Mineralocorticoids, they regulate ion concentration. Aldosterone will influence now the absorption of sodium and kidney tubules, thus regulating the retention of water in the body. And of course, we have the sex hormones. Sex hormones produced in the testes and ovaries regulate now the production of sperm, of course, and eggs, and aid in the development of the secondary sex characteristics. So that is the topic on the chemistry of lipids. These are just the different structures of cortisol, cortisone, prednisolone. We have prednisone, aldosterone, and we also have here testosterone. We have also estradiol, estrone, progesterone, and we also have the metanandrostenolone, which is also a synthetic anabolic steroid. So this is just for you to appreciate the different structures of what we have been able to discuss. So again, that is our topic on the chemistry of lipids. And I hope that you can be able to learn something from this topic as your last remaining topic for midterms. Thank you and God bless.